Okey, Assalamualaikum dan salam sejahtera semua. Diharapkan semua kini berada dalam keadaan yang sihat sejahtera hendaknya. Hari ini kita teruskan tajuk ataupun pengajian kita untuk khusus KM3443, iaitu berkaitan dengan pengukuran suhu, or we call as a temperature measurement. Saya rasa you all quite familiar with this type of measurement currently during COVID time ni, kerana di mana-mana tempat yang you all pergi akan disediakan temperature detector untuk detect ataupun untuk capture the temperature body pada badan you all lah. So you all dah tahu the advantage of this measurement, this device. Cumanya untuk topik kali ini kita akan lebih pergi kepada what we call the theory of the temperature measurement. We want to know what type of sensor that available in order to capture the temperature measurement, and then apakah the limitation of the temperature measurement with respect to the different resistance of the materials. So kita akan pergi secara detail mengenai itu. Dan satu perkara yang saya nak share di sini yang sangat menarik. You all tahu kalau temperature detector yang berada dijual di pasaran yang harganya tak berapa mahal, ataupun you all boleh pergi ke supermarket ataupun kedai-kedai runcit yang menggunakan temperature detector yang ada tu, kenapa the temperature detector itu ada limitation, iaitu maksud saya the device can only be used only for a 10,000 click, means that if you click for 10,000 time, so after that the what we call the measurement, the device is not accurate anymore, and then need to get a calibration untuk further further use lah. So kenapa kenapa certain temperature device ini ada limitation dia. So dalam tajuk ini kita akan dapat merungkai mengapa fenomena itu terjadi, dan kita tengok di di tempat-tempat orang ramai, seperti contohnya di airport ataupun di terminal station mana-mana, dia ada sediakan what we call as temperature detector using a camera temperature detector. So itu pakai konsep apa? Adakah dia menggunakan radiation energy ataupun dia menggunakan infrared? So that will be discussed in this chapter lah. Okay. So from that, at the end of this chapter, a student will be able first to describe the primary standard for temperature, second, state the role of fixed point calibration and the necessity for interpolation method in establishing the temperature standard. The third one, describe and analyze the thermal expansion thermometry. And fourth, employ standard relationship to determine the temperature from a resistant device. Fifth, analyze thermoelectric circuit designed to measure a temperature. Sixth, describe the experiment to determine the thermoelectric potential for material pairs. 7. State the principle employed in the radiation temperature measurement. And last but not least, estimate the impact of loading errors in a temperature measurement. Okay, kita teruskan. Okay, now we go to the standard and a definition of a temperature measurement. Okay. Temperature is described as the property of an object in hotness or coolness. Okay, it's very straightforward. Three essential aspects of a temperature measurement: either definitions of the size of the degree, Second, fixed reference point for establishing a known temperature. We need our reference point in order to establish the temperature changes, right? And third one, a mean for interpolating between this fixed temperature point. Okay, the modern engineering definitions of the temperature scale is provided by a standard called as the International Temperature Scale of 1990, or we call as ITS 19. Okay, they have their own standard that need to follow when we talk about temperature measurement. Sorry. Okay, now we go to the basic. I think you guys quite familiar with this thing. This is very basic, very fundamental. How the conversion between the Fahrenheit to the degree Celsius. You know how to differentiate between the Fahrenheit, the differentiate of the Celsius, and how about the differentiate between the Kelvin, right? So there has a definition on each of the units, okay, here. So I just go through because this is very straightforward and it's a very fundamental. Okay, so the principle of a temperature sensing, the temperature sensor principle, kita ada 4 jenis. Either using the material expansion based on a change in length, volume or pressure. For example, a thermometer yang kita pakai dekat lab ataupun dekat dekat a simple measurement yang kita nak buat dalam seharian. Most of them kita pakai thermometer, iaitu menggunakan thermal expansion. Okay, the second one is a change in the electrical resistance. So kita determine the resistance of the resistance of the temperature. So we call as or we refer to the RTD or thermistor. Okay, and then the third one, if we refer to the contact voltage between a two dissimilar metal. If you have a two different metal contact each other and you refer to the voltage of that, so that is the one of the type of the sensor to detect the temperature, or we call as, for example, is a thermocouple. Okay, this is a thermocouple equipment. And fourth, if we see they have a different change in the radiated energy, so that is one type of the principle also in order to sense the temperature. For example, as a radiation based temperature detector or pyrometer. Okay, now we go to the first one, the thermometry based on a thermal expansion. Okay, the first one is a liquid in glass thermometer. Yang ini saya rasa setiap you all pernah pegang, pernah menggunakan device ini, equipment ini. Okay, memang kebanyakannya ada di lab science masing-masing di sekolah. Okay, liquid in glass bulb thermometer first experimented by Galileo in 1592. Okay, a little bit about the history. Liquid in glass thermometer measures temperature by virtue of the thermal expand of the liquid. The bulb serves as a reservoir and provide a sufficient fluid for the total volume change of the fluid to cause a detectable rise of the liquid in the stem of the thermometer. Right? This is just a very straightforward one, and it's really easy to understand. And then the difference in the thermal expansion between the liquid and the glass produce a practical change in the liquid in the level of the liquid in the glass capillary. Okay, this is examples, pictures of the liquid in glass thermometer. Okay, during calibration, such a thermometer is subject to one of three measuring environment. Okay, the first one is for a complete immersion thermometer. The entire thermometer is immersed in the calibrating the temperature environment or fluid. And the second one, for a total immersion thermometer, the thermometer is immersed in the calibrating temperature environment up to the liquid level in the capillary. Okay, and the third one, for the partial immersion thermometer, the thermometer is immersed predetermined level in the collaborating environment. Okay. Okay, now the second one menggunakan thermal expansion ini, iaitu bimetallic thermometer. The physical phenomenon employed in a bimetallic thermometer sensor is the differential thermal expansion of a two metal. Okay. If we can see from figures 2 here, shows the construction and response of the bimetallic sensor to an input signal. The sensor is constructed by the bonding of two strips of a different metal. You can see from here they have a metal A, metal B. They have quite different. They have quite variety of the shape of the bimetallic thermometer is either strip, spiral, or helix form. Okay. The resulting bimetallic strip may be in a variety of shape depending on the particular application, as I said before. Okay. And then continue at the assembly temperature, the T1, the bimetallic strip will be straight. However, for the temperature other than T1, the strip will have a curvature. The physical base for the relationship between the radius of curvature and temperature is given by this formula. So you can see from this formula the relationship between the radius of the curvature and also the temperature different between two different strip of metal. Okay, that is for the bimetallic thermometer. Okay, and then we go to the second one, which is the electrical resistant thermometer. If we have a different resistant electrical based on a temperature, so the electrical resistance of a metal conductor change with temperature. Okay, the temperature dependence of the resistivity of the material. Okay, suhu bergantung kepada resistivity of the material, the resistance of the material. Two basic class of a resistant thermometer: resistant temperature detector, what we call as RTD, conductor, or thermistor. Thermistor is a semiconductor. Okay, the resistance change of the thermistor may be expressed as this one, this formula. Okay, when K is the temperature coefficient. A thermistor can be divided into two types, which is either PTC or NTC. What is PTC or what is NTC? PTC is a material are metal and alloy. However, for the NTC is material are semiconductor. The further difference of two different type of thermistor here will be discussed later in the next section. Okay. Okay. So from this graph, figures 3, resistance as a function of temperature for selected material used as a temperature sensor. So you can see from here, different material will produce a different resistance with respect to the temperature changes. So if you want to design your thermistor, you need to make sure your materials selection is good in order to get the good resistance for your application lah. Okay, now we go to the RTD, resistant temperature detector. In the case of the resistant temperature detector or RTD, the sensor is generally constructed by mounting a metal wire, as you can see from here, okay, on the insulating support structure to eliminate the mechanical strain, and by encasing the wire to prevent changes in resistance due to influence from the sensor environment, such as corrosion. And figures 4 shows the typical RTD construction. Okay, it's very straightforward. The relationship between the resistance of the metal conductor and its temperature may be expressed as the polynomial expansion, as mentioned as here. For metal, RT relationship, the resistance temperature relationship can be approximated by the quadratic function. So this is the general knowledge for you all. No need to remember, and you need to understand. You need to know if they are mentioned of this equation. So what that refer to. Okay, so example, if you want to find the resistance, so you have your R0, your initial resistance, so you have your alpha, alpha, beta. Here are the material constant, and you can see the difference of the temperature measured in the materials. Okay, so the approximation can be expressed of this equation, which is R equal to R0 column 1 plus alpha T minus T naught. And what is alpha here? Alpha is the temperature coefficient of resistivity. From here, what we want to explain is, you can see three different type of the materials, right? Shows a different relative resistance with different temperature. Okay, setiap material yang berbeza mempunyai relative resistance dan juga reflect pada temperature yang berbeza-beza. Okay, it's up to you what type of the material that you want to select for your system, for your temperature system device, for example. Okay, mechanical strength can be changed a conductor resistance and therefore must be limited. Okay, the mechanical strength ni kita kalau boleh kita elakkan semasa semasa capture the temperature with respect to the electrical resistance. Okay, the platinum is the most common material chosen for the construction of RTD. Okay, this is a platinum that I shown to you. Okay, platinum, okay, due to the predictable and reproducible change in electrical resistance with temperature, which can be calibrated and interpolated to the high degree accuracy. Okay, mostly for the RTD materials part, the main part we use, most industrial players use a platinum because of the advantage of the advantage of the material, because can be calibrated and interpolated to the high degree of accuracy. Okay. Okay, ni di sini kita table 1 shown a temperature coefficient resistivity, the alpha here. If you can see, different material have a different temperature coefficient resistivity, will reflect to the numbers of the resistance of the system. So different materials will perform a different number of resistivity. Okay. Okay, this is the example that available in the industrial market. Example of RTD using the platinum. Okay, it's very, what's the advantage for this type of RTD? It's a very high stability using a partially supported wire wound construction. The pre-age at elevated temperature, that's good, and is suitable for negative 200 degree to positive 600 degrees Celsius. It's a very good range. Size from 0.75 millimeter diameter to 4.8 millimeter diameter. It depends on your application, what for. Length from 8 mm to 30 mm, and then the typical tolerance is plus minus 15% degree, 15 degree or plus minus 30 degree at a 0 degree fairly, and withstand a 300 gram in the range of 10 Hz to 1 kHz. Okay. And this is one example also for the platinum thin film RTD lemon, fabricated using a state-of-the-art thin film processing technique, and then the limit of the temperature is negative 50 to 600 degrees C, and generally thin film RTD element are incorporated into some type of assembly for protection. Extension lead may be attached by soldering, crimping, brazing, or welding. The attachment method must be capable of withstanding the intended maximum operating temperature. Okay. So we want to see the operations of the RTD, how it works. Normally the response time is about 0.5 to 5 seconds. Okay, governed by the thermal conductivity. Depends on your thermal conductivity of the materials. Okay. Operating range for RTD depends on the type of wire. If you use the platinum, it's about -100 to 650 degrees C. Or if you use a nickel, it's about -180 to 300 degree C. Okay, and then they use a bridge circuit in which the null condition is accurately detected. I'm sure that you quite familiar with the bridge circuit previous topic that teach of Dr. Rizayuddin about the electrical circuit, and right, so you have the kind of idea when I talk about the bridge circuit here. Okay, this is what I call before. Okay, the RTD resistance measurement, the Wheatstone bridge. Okay, this is type of the Wheatstone bridge circuit, or WBC, sorry, are used to measure the resistance of RTD to minimize a loading error and provide a low uncertainty in measure resistance value. However, the basis of the WBC does not compensate from the resistance of RTD, which is the major source of error in electrical resistance thermometer. Therefore, to achieve a greater accuracy, 3-wire and 4-wire circuit are used. So if you can see from figure 6 here, ini adalah bridge circuit untuk Wheatstone bridge yang basic, and then when they add some lead wire here, so they can overcome the problem of the error of the electrical resistance thermometer. Because what? Because you want to achieve a greater accuracy for the system. Okay, so there some innovations there when they put the lead wire in the bridge circuit. Okay, so they come up with the equation. So at balance condition, neglecting a lead wire effect. So from here, the effect from the lead wire effect. So we neglect that one. So we get the relationship between R1 over R2 is equal to R3 over RRTD. Okay. So from here, so R1 over R2 is equal to R3 over RRTD. Okay. If our condition include the effect of the lead wire resistance, so it might be like this: R1 over R2 equal to R3 plus R1 over RRTD over R3, which is the R1 R3 here is come from the effect of the lead wire. Okay. Okay, now we go to the example for more understanding. An RTD form one arm of equal arm Wheatstone bridge as shown in figures below. Okay, you understand this circuit. The fixed resistance R2, R3 are equal to 25 ohms. Okay, that's fine. The RTD has a resistance. The RTD here has a resistance of 25 ohm at a temperature of 0 degree. So this is your T node, and it's used to measure a temperature that is steady in time. Suppose your alpha coefficient or resistance for this RTD is 0.003925 degrees C minus 1. A temperature measurement is made by placing the RTD in a measuring environment and balancing the bridge by adjusting R1. Okay, the value R1 required to balance the bridge is 37.36 ohm. So determine the temperature of RTD. So this is the example of the question that might be question in your final. So this is one type of bagaimana dia tanya you all bagaimana dia bagi you all circuit, and then dia tanya what is the temperature for at R1 for example, or temperature of RTD. So you need to know how to find that. It's very simple. So you familiar with this equation that I told you before here. Okay, you need to understand, okay, the approximation expressed here kan. So you need to know how to use that. So the relationship is R1, okay, R1 over RTD is over R1, over R2 is equal to R3 over RTD. R1, okay, over R2 is equal to R3 over RTD. Okay, you know how to get the relationship, right? So, okay, this is given to you. RRTD is measured to be 37.36 ohm, as mentioned here, okay? And then, R naught is 25 ohm, at a T naught is equal to 0 degree, and alpha is given to you. So just use directly the equation given to you, okay? RRTD, how you get to RRTD? So you have your 37.36, you have your R naught, the 25, and you have your alpha. So T minus T naught, which is T naught is 0. So you will get your temperature at RTD is about 1 to 6 degrees C. I recommend you to try at home, try yourself, and you will get the answer or not. Okay. Okay, now we want to go, before this kita pergi kepada thermistor. Okay. Because as I said before, thermistor dia ada dua jenis, ada RTD ataupun menggunakan dia ada conductor ataupun semiconductor kan, menggunakan resistance different. So now we will go to the bulk semiconductor sensor, or we call as a thermistor. Okay. A temperature transducer whose operation relies on a principle of change in a semiconductor resistance with change in a temperature, highly non-linear. Alright. Typical temperature range is about 250 to 650 degrees C. High sensitivity is 10%. Resistance change per degree C is common. It's very good. Measure by a bridge circuit with a null detection. So we need to use a bridge circuit before this and apply it into this condition. Variety of configuration in many form of disc, bit, rod, or varying size. And it's a very fast response time, but increased with encapsulated for protection against the hostile environment. Response time will be longer. Okay, this is the criteria for the thermistor. Okay, as I said before, the thermistor have two different type, which is the NTC and PTC. Okay, what is the difference between that type? Okay, for the NTC, when the resistance decrease with an increase in temperature, the result is a negative temperature coefficient. I repeat again, when the resistance decrease with the increase of the temperature, the result is the negative temperature coefficient. Okay. However, for the PTC, when the resistance increase with the increase in the temperature, the result is a positive temperature coefficient. Okay, I believe that this is very easy for you guys to understand. Okay. As usual, we come up with the relationship form between the resistance and temperature for the thermistor. So this is the thing that you need to remember, that you need to understand. How they calculate for the resistance is equal to R naught E beta 1 over T minus 1 over T naught for the thermistor. So what is B? B is the range between 3500 to 5600 Kelvin, depending on a material's temperature and individual construction of the sensor. Okay, so when refer to the figure 7 here, so different material will give you a different range of the beta. So will appear also the different of your resistance with respect to the temperature. That I mentioned to you before. Okay, sama saja konsepnya. Okay, now we want to go the phenomena of delaying current through a thermistor. Why adanya berlakunya fenomena perlambatan arus dalam thermistor. Okay. Sorry. Okay, when a voltage is applied to the thermistor, okay, its initial resistance is high. Okay, faham? Therefore, a limiting current flow. Correct. As the thermistor body temperature rises from a self-heating, the resistance drops while the current continues to rise. Yes, it's absolutely. This cycle continues until a point of current saturation is reached and limited by the applied voltage and the initial circuit resistance. A larger body thermistor will have a greater mass and consequently a larger dissipation constant, which in turn will slow down the time required to reach the steady state condition. So all this thing is illustrated by this graph. Okay, so from here you can see as increasing of the time, so akhirnya kita akan tengok dekat sini dia akan berlakunya steady state for the current. Okay, the zero power resistance of a thermistor is the resistance value of the thermistor with no flow of electric current. Okay, the dissipation constant of thermistor is defined as the given ambient temperature, or we call as this one is equal to, the dissipation constant is equal to P over T minus T infinity, when P here is a pressure. Okay, if I'm not mistaken, let me check. The P here is the power, sorry, P here is the power supply to the thermistor. Okay. Okay, now we go to the exercise 2, but now I need you to try at your home. Okay, this is very straightforward. I think they got the answer or not. Oh, we got the solution here, so it's okay, we do together. The material constant B is to be determined. You still remember what is B? Okay, this is B. Okay, this is B. Different material have a different beta. Okay, figures below A. Okay, this is A here, thermistor. The thermistor has a resistance of 60 kilo ohm at 25 degrees C. The reference resistor in the circuit R1 has a resistance of 130.5 kilo ohm. The dissipation constant is 0.09 megawatt per degree C. The voltage source used for the measurement is constant is 1.564 volt. The thermistor is to be used at temperature ranging from 100 to 150. So you have your range of temperature between 100 to 150. So in a solution you can do 100, 125 and 150. So you have three range of the temperature, right? And then determine the value of beta. Okay, so this is given to you in the question. So the temperature range of interest is between 100 to 150 degrees C. Okay, you have your R0, which is 6000 ohm. Your T0 also 25. You have your EI, which is your where is your EI here, which is your 1.564. Please not confusing. E here is not a current. Okay, E here is the voltage. Okay, the voltage. Okay, and R1, where is R1 is equal to 130. This one is R1. 130.5 kilo ohm, and also you have your dissipation constant, which is 0.09 megawatt per degree C. So it's very straightforward for you. Okay, as I mentioned before, you need to do a table. So you have your three range of your temperature. So you have your E1. Okay, the E1 is given to you. Where you get your E1? Your E1 will, you will get your E1, okay, from the laboratory oven and measuring the temperature of the oven. So this is given to you, don't worry about that. Okay, so from that you will get directly your RT by using this type of equation. So RT here, you have your R1, you have your EI, you have your E1 before this and minus 1. So from that you will get a different temperature level in different RT. Okay, okay, so after that, so the question asking you about the value of the beta. So from here, okay, you need to improvise a little bit about this equation and then make it like this. I think you're quite familiar with this. You know how to do that, how you want to get the launch relation here, RT of R0 over beta, 1 over T minus 1 over T0. So from here, direct, you will get your beta by substitute all these things. You have your RT already, you have your R0, you will get this term. You have your beta, it's okay. This one you got also, okay, with a different condition of temperature change. So directly you will get your value of your beta. Okay, and also I suggest you to try by your own, and then you will see how the equations works in your solution. Okay. Okay, because in this topic we have a lot of slide, and then I think better for me to separate the slide into part 1 and part 2. So that's all for only for part 1. We will see you for the next video for part 2. Stay tuned, and assalamu alaikum.